Just want to say welcome everyone to South Park Commons as part of our 2018 AI Technical Speaker Series. I want to introduce Stefano Ermon here. So very quickly about me and about the Commons. Joe and I are the co-organizers of this AI Speaker Series. This is the second year we're doing it. We try to cover a lot of different topics. This year our focus is on the impacts and implications of AI. This is sort of the beginnings of the series, but we'll have more in later months as well. So if you're interested in that, feel free to follow up with me later. Personally, I run in machine learning for social impact consultancy, so I'm really passionate about a lot of the work that Stefano is doing, a lot of his research, which you'll get to hear about. And speaking of which, he's an assistant professor at Stanford University in computer science as part of the AI lab. He's a fellow with the Woods Institute of the Environment. He's done a lot of work sort of championing this new field of essentially computational sustainability. And he'll be talking with us today about predicting economic well-being and ultimately eradicating global poverty. So with that, Stefano.
Yeah, it's great to be here, and yeah, I'd like to keep the talk as interactive as possible. So if you have any questions at any point, feel free to raise your hand or interrupt me, and I'm happy to take questions at any point. Right. So so as Yannick was saying, what I'm going to do is I'm going to give you a little bit of an overview of the kind of research my group has been doing at Stanford on using AI to address global sustainability challenges. So as you are probably aware, our society is facing some pretty formidable challenges to sustainable development. There's close to 1 billion people around the world living in extreme poverty, hundreds of millions of people that don't have to eat every day. Climate change is real, it's kind of like threatening the survival of many societies around the planet. We're going to need to find new sources of affordable and clean energy, find ways to close the gap between developed and developing countries, find ways to reduce inequalities, and so forth. But clearly, these are very, very important problems. They were also recognized by the international community, by the UN, as the ones you can see here, that the 17 Sustainable Development Goals are sort of like being the key priorities that the international community should be focusing on until sort of like 2030. And so clearly these are very, very important problems. They're also very, very challenging. And one of the reasons, not the only one, but one of the reasons is that we actually have very little data about these kind of problems, these kind of outcomes. So this is a chart from the United Nations Statistics Division. It's showing basically the availability of the kind of indicators that we would need in order to track progress towards these very important goals. Basically, how many of these indicators are available over time. And basically, what you can see is that a lot of the data that we actually need is missing. And so with this kind of data, it's very, very hard to figure out whether we're making progress towards these goals. Like, it's one thing to say we want to end extreme poverty, but if you don't have a good way to measure how many poor people are there in the world, where they live, it's very, very hard to figure out if you're making progress, very hard to figure out whether policies are working or not, very hard to also make sure that everyday operations work as smoothly as possible. And so, yes.
Why does it look like the situation's getting worse?
Well, I'm not sure, but I guess apparently, things, it's possible that they actually get worse over time. Less and less money.
Maybe we just have more goals.
That's also possible. Right. And so, this is it's a pretty depressing picture. There's a big gap, a big sort of data divide between developed countries, or literally flooded with data, and developing countries that are basically suffering from a real data drought. Now, on the more optimistic side, we're also in the middle of a technological revolution that is, I think, really creating interesting opportunities for coming up with new innovative approaches to these problems. In particular, the kind of global sensing capabilities that we have are getting better and better. If you think about satellites, they're becoming increasingly cheaper, increasingly more accurate, and so we can get very, very high resolution pictures of basically any part of the globe with increasingly high both spatial and temporal resolution. You think about social media, you think about phones and smartphones, they are sort of becoming more cheaper, more widely adopted. And again, they potentially provide a lot of information in terms of pictures, in terms of CDRs, audio records, in terms of all kinds of information that the sensors we have are actually collecting over time. Now, clearly, this data contains a lot of information about these kind of goals and these kind of sustainability goals that we're trying to achieve. One of the challenges is that the data is typically it's massive. Like if you think about the scale of the images that we're getting from remote sensing and from satellites, it's like huge. It's massive amounts of data that keep coming in, and it's also unstructured. You have to deal with text, you have to deal with images, videos, audio signals. So this has literally largely prevented its use in kind of like trying to figure out what's going on in the world at a really in an inexpensive way. And so one of the goals of my research is to try to develop AI and machine learning techniques to extract actionable insights from all of this data that is becoming available globally, and use these insights, use these outputs from these models to try to come up with more effective solutions to these very important problems. And so what I will do in this talk is I will give you an overview of some of the research we've been doing in this field, focusing on the problems number 1 and number 2 on that list of 17 goals, ending extreme poverty and addressing food security challenges. So when we think about poverty, the typical way people collect data is by doing surveys. And surveys are expensive, they cost a lot of money to do. And as a result, the poorest countries in the world typically do very few of them. So what you can see here is a map showing for the African continent, showing for every country, the availability of nationally representative surveys in the decade from 2000 to 2010. And it's color-coded, so white, for example, means that there is no survey available for that country for that entire decade. And so you go all the way from 0 to maybe 4 in a few very, very selected countries. And so you can see here the availability of basically surveys that contain information about consumption or income, and ones that contain information about assets, basically the kind of things that people own, which is another way of measuring how rich or poor people are. So as we were saying before, you can imagine that with this kind of data, it's very, very hard to track progress, very hard to inform research, very, very hard to sort of like figure out whether policies are working or not, things like that. Now on the positive side, we're getting access these days to very high resolution images from satellites of pretty much every corner of the world. And these images, they contain a lot of information about various kinds of socioeconomic outcomes that we might care to track or to measure in a global, at a global scale. Like you can see here, like a shipping yard, the resolution is good enough that you can almost see the containers, you can almost see cars and ships. You can see information about infrastructure, about roads, about buildings, about various kinds of economic activities. The resolution is getting good enough that there is enough detail in there that you can infer a lot of interesting facts about how well or not well an area allocation is doing from an economic point of view. It's not just images. Like these days, you can even get access to high-resolution videos from space. This is something that is available commercially today. It's not extremely popular. It's not, of course, the price that you have to pay if you want to get videos, so very, very high temporal resolution, is that they're going to get very, very small spatial coverage, but it's possible to do it today. And again, clearly there is a lot of, if you had access to this kind of data, it contains a lot of useful information about all kinds of socioeconomic outcomes that we might care about tracking and predict. And this good news is that the data is getting better and better. There are a number of private companies that are entering the market. Setting up satellites is becoming cheaper. Building the satellites is cheaper. Operating them is cheaper. The quality of the data that we're getting is getting better and better. And so we're getting all of this amazing data. The challenge is how do we actually make use of it? And the difficulty is that we're dealing with raw sort of unstructured data. You have to deal with images. You have to deal with videos. And the question is, how do we actually make sense of it in a way that is scalable? Like you cannot, pay people to actually look at the videos, look at the images, and figure out what's going on. We need to figure out a way to do it in an automatic way, in a scalable way. So here's where AI and machine learning comes in. In the last few years, if you haven't heard, there's been really a lot of progress in machine learning and AI, especially thanks to this idea of using what we call deep learning. So the idea is that using these deep learning methods, we've been able to make a lot of progress in a number of key perceptual problems, like categorizing different images into classes, like tracking objects moving in videos, like localizing objects in images, and so forth. And really the key innovation that enabled a lot of these successes is the use of deep learning, so the use of essentially very high capacity models that are built by stacking together networks of artificial neurons. And these models are very complex, they're very high capacity, they can be used to model very complicated relationships between inputs like images and outputs like different classes. And it turns out that if you show these models enough training examples, if you show these models enough examples of what a dog or a cat looks like, then you can train them to sort of like adjust the parameters of the model so that they get better and better over time, and eventually they're going to be able to recognize, say, new images of dogs that they haven't seen before and figure out, okay, this is a dog, and if I haven't seen a dog from this viewpoint in this particular scene, I'm still going to be able to recognize it. And so this was really a major breakthrough in computer vision and in machine learning and AI in general. It has led to very impressive results and a number of problems, in particular in terms of, like, say, image recognition. These systems are now essentially almost as good enough as what humans can do in some restricted settings, like the ImageNet recognition challenge. And so, this is really exciting because it means that we're starting to have tools that are able to kind of make sense of visual content in a pretty reliable way. And so the hope is that perhaps we can use them in combination with all these new satellite images to kind of like make sense of what's going on in these images in a very scalable way, in a way that sort of we can apply it to sort of like keep track of what's going on in every part of the world. The challenge is that images are very complex objects. They're very high dimensionals. There is a lot of variety. Think about, say, an image of a motorbike or a car or a dog or a cat. There's a lot of variety because of changes in viewpoints, in illumination, in backgrounds, and various other things. So as a result, if you want to train one of these very high capacity models, you typically need to show a lot of examples of, say, what a cat or a dog looks like before the model really learns to recognize the concept and figures out how to recognize that object in very different scenarios. And so the challenge is that ideally what we would like to do is we would like to take one of these models sort of like off the shelves and apply them to these high resolution satellite images and train them to, say, predict various kinds of socioeconomic indicators that we might care about. Like, let's say, predict whether or not this particular region is going to be is rich or poor. Yeah.
A quick question: is it recognizing it as a dog, or is it recognizing it as must be a dog because it's not a cat and it's not a honey badger and it's not a...
Well, you can formulate the problem in different ways. One way to think about it is that there's a single class and you just have to bin it and just assign a label, or you can consider more complicated problems where you say there could be multiple objects and you need to identify all of them. Sometimes you also want to figure out where it is in the image. There are different kinds of tasks that you can consider, or maybe count different kinds of objects in an image. They can be pretty much all formulated in this same framework where you show examples, you show the model what's the correct output that you would like to see, and then you basically figure out, are you doing well or not in this particular example. If you're not doing well, then there is a procedure, a mechanical procedure that you can use to adjust your model and make it better. And so if you repeat this process a sufficiently large number of times, eventually the model will learn and it will figure out how to solve the task in the right way. But the number of examples that you have to show could be extremely large. Yeah. So yeah, and that's basically the challenge. The challenge is that ideally we would like to use one of these models off the shelf and try to train them to solve the tasks that we care about. The problem is that we don't have enough training data to use one of these models off the shelf, right? The reason we're trying to build these models is that because we don't have enough data on, say, poverty or food security outcomes this kind of sustainability applications, we typically have very limited amount of labeled data, labeled examples. And so what we had to do is we had to come up with some new approaches to kind of like get around this data scarcity problem and figure out ways to combine sort of like these state-of-the-art neural network models with some new techniques so that we can get around this data scarcity and still learn how to do a good job in these tasks. Yeah.
Is it data labeled scarcity, or are you, for example, working with companies like Spire or some of the satellite companies that might be able to provide some of the high resolution data in a more cost-effective manner?
So yeah, we're thinking about, so there is essentially the setting is that you have access to as many inputs as you want, right? Like there's essentially an infinite amount of unlabeled data, it's just satellite images. What's expensive to get is the corresponding like ground truth measurement. Like, is this area rich or poor? Are there houses in this image or not? How many cars are there? That's hard to get, that's expensive. Maybe if you just want to recognize houses, maybe you can put it on Mechanical Turk, and you can pay Turkers to do it. Even that's not straightforward, but it can be done. If you actually want to know, how rich or poor that area is, you actually have to send people on the ground, and that's very expensive. So that's why we have a very limited amount of actual that kind of training data.
Got it.
Yeah. Other questions? Yeah.
Okay. So I've heard about some other applications of satellite data for detecting deforestation, and I'm wondering if there's going to be a group of folks working together across the sustainability challenges, that maybe if one group is doing labeling, then that could be reused by another group. So I don't know if there's cross-collaboration in this way, or...
Right, so people are starting to, one of the things that really drove a lot of the progress in, say, standard computer vision applications was the development of these benchmark challenges, like there is 1 million images of 1,000 different classes of between cats and dogs and cars and whatever. Try to do as best as you can, and people were able to improve the models dramatically over the years, and then they were able to kind of use that data in different domains. Like after you train your model to do a good job on, say, on this ImageNet benchmark, then it turns out that it can do reasonably well on a number of other problems. So people are starting to do that just very recently for satellite images. There is a competition going on right now called the Deep Globe at CVPR on basically which is sort of like an ImageNet for satellite images, trying to kind of recognize different kinds of objects and doing segmentation. A few challenges. There's another one by the intelligence community, and that one even has some pretty sizable kind of prize money attached to it. I think it's just opened like 2 weeks ago. That one is about identifying different kinds of objects again. And there they provide you the data, they provide you the labels, and the hope is that maybe and they make it public available. Hopefully the models will get better and better, and we'll be able to kind of like share across different tasks. Yeah.
The question is an area of virtual force. Is there a temporality issue? So for example, like I do work in sub-Saharan Africa, and what things look like after harvest are very different than what they look like or in a good year versus a bad year.
For
the
sure.
range is wide within what we consider forest.
So ideally, yes, that's the dream would be to be able to track these kind of outcomes with very high spatial and temporal resolution. At the moment, the kind of training data that we have, the kind of surveys are done based on, I believe, some sort of like annual averages. And so that's the kind of thing we're going to try to predict. But ideally, the images that we get are updated very frequently. Maybe every day, maybe every week.
Survey time
Yeah.
to be able to
And so ideally, we would like to be able to track the changes over maybe across years, maybe even monthly. It's kind of like it's getting harder and harder, but maybe it's possible. We haven't been able to do it. We can only do track variation spatially, basically say whether an area is richer or poorer than some other area. We have not been able to. We haven't tried actually to track variation over time because the data is even scarcer. That's something we're actually working on. But yeah, that's a great point. Right, so how do we get around the data scarcity? So one thing that we did is something called transfer learning. So the idea is that there is this task that we want to solve, go from images to poverty measures. We don't have enough training data to do that. So what we're going to do is we're going to set up a different task, a proxy task, that is somehow related, like trying to predict something else from satellite images. And we're going to set up these tasks so that we have a lot of training data. So we're in the regime where these kind of deep learning models really shine, they work very well. And the hope is that by training a model to go from A to B, we're going to learn something about satellite images, what they look like, and then we're somehow going to be able to transfer the knowledge and be able to solve the task that we care about, which is to go from A to C using a lot less training data. So what could a good proxy task be in this case? Well, what we thought about is that nighttime light intensity could be a good proxy for economic development. It turns out that we have satellites that take images of the Earth not only during day, but also during night. And the amount of nighttime light intensity can tell you a lot about how economically developed an area is. So for example, this is an image of a certain part of the world taken during night. Can anybody guess where this is?
Yeah, that's Korea.
Thailand.
Right.
Korea, actually. It looks like an island, but it's not. This is actually South Korea, and this part here is actually.
Oh, wow.
So it's basically almost entirely dark. Probably that's just the capital. So clearly, there's a lot of correlation between economic development and how bright, essentially, a particular location is. And so the hope was that perhaps we can exploit this information to train our models. And so what we did is we used this transfer learning idea. We said, well, the nice thing about this kind of data is that you basically have an infinite amount of training data. You can pick any location in the world that you care about. You can take the corresponding daytime image, and you can take a daytime image and the corresponding nighttime intensity. And you can ask your neural network to try to predict how bright a particular location is going to be just by looking at how the location looks like during day. So maybe you show it a map of some kind of forest, an image of some kind of forest, and the network should say, oh, I think that will have low nighttime light intensity, and then you show it some kind of how you develop the urban area, and then I should probably predict that that area is going to be bright at night. And the nice thing is that you can basically generate a training set as large as you want. You can just sample hundreds of thousands or millions of locations across the world. You look at the daytime image, the corresponding nighttime light intensity, you generate your training set, and you train your model to predict nighttime light intensity from daytime images. Yeah?
Sorry, does population density matter in this case? Like you can have 3 houses putting out a lot of lights versus a village putting out the same amount of light in the same area. And
Yeah.
The 3 houses.
So definitely, it does matter. In fact, essentially, what the model should be able to do is to try to figure out, how densely populated an area is, how distributed it is, and hopefully, by doing that, it will learn to identify houses, roads, various kinds of things that we think are going to be essentially measures of infrastructure development, and then we can use those measures to predict something else. Right? And so then, basically, what you do is you train your convolutional neural network, which you can think of it as some kind of mapping from images to, say, the amount of nighttime light intensity. And what you do is, effectively, you look at the last layer of this network of neurons, and you can sort of think of the last layer as being some kind of high-level representation of what's going on in the original image. You can think of them, call them features. It's kind of like some kind of visual cues that are useful for predicting, how bright or dark a location is going to be at night. And the hope is that the features, these visual cues that are predictive of the amount of nighttime light intensity, will also be useful for predicting, say, poverty or whatever it is that we want to train. And it turns out that it does. The features that the model discovers are actually reasonable. They are actually very semantically meaningful. So what we did is we picked a few of these features, of these functions that the model learned to identify in the visual images, and we tried to look at what they look like. So what we do is we take an image and we look at which pixels in the image are very important for that feature. And then by visually inspecting the images, we can sort of figure out what these features actually represent, what kind of visual cues the model is looking for when trying to predict the amount of nighttime light intensity. So here are some examples that of the kind of features that the model learned to identify. We see that it learned how to identify roads, bodies of water, traffic roads, tall buildings. My favorite one is the swimming pool filter. So the model learned that in order to predict whether an area is going to be bright or dark during night, looking for swimming pool is a good indicator, right? It's going to be a fairly rich area, and so that's a good feature to look for. And what's interesting here, what's exciting, is that we never provided any label, any example of, okay, this is a road, this is traffic, this is a swimming pool. The model figured this out by itself just by trying to predict, by trying to solve this task of predicting nighttime light intensity. Right? So that's pretty exciting because the features are sort of like semantically meaningful, but we didn't really have to provide any kind of manual label. So it's a very sort of like inexpensive way to learn how to recognize different kinds of indicators of infrastructure development without actually having to spend a lot of time providing labels.
What role does the pattern of the light play? What role does the pattern of the light play? Like if the lights are in a square or the lights are around a circle like a pool or something.
So the resolution is actually we don't actually see, like the amount of nighttime light intensity is not, let's say, like a meters resolution. It's just pretty bad. It's like in the order of hundreds of meters. So it's more like it predicts how bright or dark an entire area is going to be.
Okay.
So the resolution is not good enough.
Okay.
For actually looking at the numbers. Right. So now in principle now what we could do is we could try to take, say, a country like, say, Uganda, and then we could try to, let's say, get images that essentially cover the entire country, then feed them into the model and try to predict, let's say, poverty. Now, one thing that we know is that we're trying to predict something that has a lot of spatial-temporal structure. We're trying to predict something that we know changes fairly slowly over time and to some extent over space. So the idea is that we would like to also model this. We would not want to just make predictions independently at each location, but we want to somehow tie all these predictions together. And so maybe I'm not going to go too much into the detail, but what we did is we combined these kind of deep learning models with some more statistical models from both machine learning and sort of like geostatistics community, something called the Gaussian process. I'm not going to go too much into the details of how that works, but sort of the idea is that the model sort of looks like this. You have different locations for which you have images. They are fed through a neural network that will extract these visual features and will try to make a prediction. Then there is an additional layer that will basically be used to make sure that all the predictions are sort of like consistent with each other. It's basically enforcing the fact that we know that these outcomes that we're trying to predict are correlated over space and time. And the advantage of this is that you can still train it end to end. I'm going to skip this part. Another interesting thing that it lets you do is it lets you quantify uncertainty. So given a new location, the model will not only be able to tell you how rich or poor, let's say, that location is going to be, but it also allows you to quantify how uncertain the prediction is. It will basically tell you that maybe in some locations the model is going to be more confident, in some locations it's going to be more uncertain about it. And so it turns out that you can use this to come up with some new semi-supervised learning scheme. So the idea here is that while we have very few labeled examples, we have very few locations for which we have a ground truth measurement of how rich or poor that location is going to be. We have essentially an unlimited amount of satellite images without the corresponding poverty label. And so what we can do is we can try to leverage the fact that we have a lot of unlabeled data and try to make the model better. And the way we do it is essentially by saying, given that we have a way to quantify uncertainty in our predictions, what we can try to say is we can take a location for which we don't have a ground truth label. We can check what kind of prediction the model gets. We don't have no way of validating whether that prediction is good or bad. What we can say is we can try to change the parameters of the model so that essentially the predictions will have less uncertainty. So the model is going to be more confident in the prediction that it makes, in points for which we don't have an actual label. And so it's sort of like, you can think of it as kind of like trying to move these points around so that the predictions that it makes have less uncertainty. So one way to think about what's going on is that we're essentially forcing the model to look for features that are not only good at making predictions at the points for which we have labels, but are also sort of like occur often in images for which we don't have labels. And that sort of like encourages, it's a form of regularization that helps the model learn better features. I went through this very quickly. You can read the papers if you want to learn more, but it turns out that this really helps with the predictive accuracy of the model. And so we can now essentially use the model to make predictions and see how well the features that we discover using the pre-training step, using nitroids, plus this Gaussian process model, we can see how well it does at making predictions about how rich or poor different locations are going to be just by looking at the corresponding satellite images. So what we did is we took several countries in Africa. Let's say here I have the example of Uganda. We took the survey data that we have for the country. Each dot here corresponds to a location, say a village. And what we do is for that location, we collect images, and then we try to make predictions for how rich or poor that location is going to be using our model. And because we have actual ground truth measurements for that point, we can check how accurate the predictions are going to be. So what I'm showing here is for each point, I'm showing both the actual asset score, which is kind of like a measure of how rich or poor that location is based on the kind of things people own. And at the same time, I'm also showing what's the prediction made by the model. And so ideally, you would want to see the points on this straight black line. That would mean that for each point, the prediction is the same as the actual ground truth measurement. You can see that it's not perfect. There is some variation. There is some variation that we're not able to capture. There are some points that are far from the diagonal, meaning that the prediction is not correct. It's off by a little bit. But we capture something like 70% of the variation in the data, which is extremely good. It means that you can predict a lot. You can get very, very high predictive accuracy. You can basically figure out whether locations are rich or poor just by looking at the corresponding satellite images. And sort of like this was really sort of like something that my colleagues that we were working with in the economics department that were thinking a lot about these problems, they couldn't believe that we could get this kind of accuracy. Like it was really, really extremely good. Previous studies that were using CDR data, so like phone metadata, basically information about who's calling who, and so very, very privacy kind of like sensitive data, they were not able to get as good as this kind of predictions. Yeah.
I'm just curious, is there anything interesting visually about the really off-diagonal points? Because this is sort of a model that's looking for salient visual features, and so there might be some kind of statistical or visual regularity.
Yeah, so first of all, there are several things to consider. One is that even the measurements that we have are noisy because they're collected by surveys, and so there's noise in the measurements. The other thing to consider is that there are just things that you cannot see from the images. Like this asset score is based on things like how big is your house, do you own a refrigerator, do you own a TV, do you own a bike, these kind of things. And some things you can maybe get from the satellite, like how big the house is, what kind of roof they have, what kind of vehicles they own. There are things that you cannot see from the images, right? And so there's some variation that we cannot hope to be able to capture using the model. Then there's also the fact that we are not doing for sure not doing a perfect job at actually training the model. It might overfit, and so then there's also that sort of source of error. And so we couldn't figure out any particular pattern in the sense that we always make mistakes because of this feature, but it's possible that we just learn how to make predictions based on just over. We don't think it's overfitting, but it's possible that it's just imperfect. Yeah.
How far do you expect this to, or how far does this seem to generalize other, between villages in the same country, between countries in the same region?
Good question, yeah. So this is basically a model that is trained in one country and tested in the same country. So the way to think of it is that you take a point, you build a model based on everything else, and then you try to make a prediction at that point, pretending that you haven't seen it.
Got it.
Now, what we did is we tried experiments where we said, okay, we train a model in one country and we test it in a different one.
Yeah.
And that, let's say you train in Tanzania and you test in Uganda.
Mhm.
And that works not as well as you would expect, but it's still doing reasonably well.
Mhm.
At least if you are geographically not too far away. Like say we tried Uganda to Nigeria, that doesn't work too well. Like if you go from East to West Africa,
Yeah.
that doesn't work too well, but it's still doing reasonably. Okay. The best is basically to train and test in the same country or to pull together all the data. That also works pretty well. Just put everything together, fit a single model, that works pretty well.
Is that because the definition of wealth might be different? Like one culture likes goats, the other likes cars, or?
That's part of the problem. So there is some pre-processing that is done to try to basically put them in the same unit of measure.
Right.
But yeah, that's part of the problem. There's some coverage.
Have you considered looking at more discrete things like population? So potentially you could just take a satellite image, you know in advance what the population is, like a transfer learning thing.
Yeah, so we have some projects going on population. We can actually do pretty well, not surprisingly. It's not published yet, but yeah, we've been able to get some pretty good results that we're looking for. I know Facebook has been doing some project in that space too, where you actually track buildings, but they were mostly kind of like trying to disaggregate. Like, let's say they have some census data, maybe at the regional level or district level, and they try to disaggregate by basically counting buildings and figure out where people live within that region.
It'd be very useful for migration trends.
Have you tried making the same chart using just the nighttime light data?
Yeah, so yeah, that's good question. Yeah, so if you just try to use night lights, it works a lot worse than this. And the reason is that there are a lot of locations that are completely dark at night, but there is a lot of variation in how rich or poor they are. So if you just use night lights, you're not going to be able to distinguish them. But if you look at the corresponding daytime images, then you're going to see that there are features that are predictive of these kinds of things.
So to piggyback off Nick's question, what else goes into studying migrations, not just poverty, but predicting migration patterns?
Yeah, definitely population. One thing that we're playing around with is essentially looking at refugee camps, and we're actually trying to count tents. We have a nice data set that we just got from the UN on basically we have the high resolution images of refugee camps and the corresponding counts for how many tents and how many people are there. And so we're trying to see what we can do. We actually got some pretty good results there too. It's not published again, but that's another way to think about the problem.
I think I recall reading your paper, and it said you used the nighttime lights DMSP data set. I was wondering if you've tried it with like the newer nighttime light
VIRS?
satellites with VIRS.
Yeah. So we also tried that. It doesn't make a whole lot of difference. That's a little bit higher resolution. It didn't make too much difference. Right. So now the nice thing about this is that this is, although it's not perfect, the only thing that you need to make predictions are images, and images are cheap. They are globally available. They are updated frequently. So what you can do is you can take a country that you care about. You get a lot of images, basically covering the entire country. You feed them into the model, and then you can make predictions. And the predictions are have very high spatial resolution, and you can update them in a very inexpensive way. As soon as you get new images, you can feed them into the model, and you can keep the maps up to date. So we did it for a few countries. You can see them here, and that's really exciting because it's very inexpensive. It's a very scalable way to kind of like predict and track this kind of outcomes in a very on a global scale. We've got a lot of interest in this work, both from various kinds of organizations, from on the large side, like World Bank, the World Program, and so forth. Also, like people like Bill Gates was tweeting about this work when we published it. It was mentioned in the White House report on the future of AI, and lots of media coverage. One of the nice things is that the Scientific American in 2016, they recognized us as one of the 10 ideas that will change the world from 2016. So we're really excited about the interest that this work had, both from government organizations, small NGOs, and also in general the scientific community. There's a lot of interest from people in the social sciences to use this kind of data to come up with better models that can figure out what drives the variation that we see in these kind of outcomes. Is this environmental factors, political factors, or other things. Right? So really, really excited about this. Some NGOs are actually already using this. So Opportunity International is sending an app. They're trying to use this stuff to make their operations better. And so really excited about this. Now, yeah, so how much time do I have?
It's 7:30 right now, but yeah, we do have some more time, especially if we're doing Q&A as we go.
Sure, yeah. So maybe I'll tell a little bit about some of the other things you can predict using images. I promised you that we'll talk about food security. That's another big problem that we're facing today. There are a number of ways in which you can use information technology, AI, and machine learning to address food security outcomes and problems. What I will focus on today is the kind of work that we've been doing using remote sensing and satellite images to track agricultural outcomes. So monitor basically agricultural productivity. And so basically what we did is we built a similar system, a combination of deep learning and Gaussian processes, that instead of predicting poverty for different locations, it's basically trying to predict how given a location, given say some fields, how productive these fields are going to be. Basically, is this field going to yield a lot or not very much in that particular year? And so we looked at two things. We looked at crop, we looked at corn and soy, and we looked at various scales. You can either do it at the national level, you can do it at the county level, you can even do it at the field level. Within a field, we try to figure out which parts of the fields are going to be productive and which parts are not going to be productive. So what I'll show you today is some work that we did in the US, where we focused on soybean production. It's one of the main crops in the US, and this is a model that we built at the county level. So this is a map of the Midwest. It's a big soy producing region in the US. Each little square here is a county in the US. And what we try to do is we try to essentially take satellite images for that county and use that information using this deep learning model plus Gaussian processes to basically predict whether that county, what are the soybean yields going to be in that county for say in a given year. And so what we're trying to do here is we're actually trying to forecast how productive the fields are going to be. So let's say during a particular year, say 2012, we're going to get many images. As soon as we get the images, we feed them into the model, and we try to update our prediction for how productive the particular county is going to be.
How far in advance?
So I'll show you the results. So these are the results for, say, year 2012. So this is a ground truth map showing basically how productive different counties were in 2012. So here blue means low productivity, red means high productivity, so I think it's bushels per acre. So in May, we basically have the first images. We can feed them into the model, we can try to make a prediction, and you can see that the prediction is not great. The model is too optimistic. For a lot of counties, it's predicting fairly high values, where actually the actual productivity for those counties is going to be fairly low in 2012. Now if you go to say June, then you feed in, you get more images, you feed them into the model, you can update the prediction, and you can see that it's getting a little bit better, but it's still fairly off. Then in July, it's getting better, and then in August, you can see that it's getting better. It's kind of guessing, it's figuring out that the productivity is going to be low in those counties, and then in September, it pretty much gets it right. And the reason that the model was not doing well in 2012 is that it was a drought year. And so the model took a while, initially thought was fairly optimistic, didn't know it was a drought year, but then as you get data, basically figures out that it's a drought year, and so lowers the predictions, and eventually it does pretty well.
When is the harvest?
It's basically November usually, October. So this is October, yeah, and that's the last one we have. Now, how well does this model do? One thing we can try to do is we can try to compare to what USDA does. So it turns out that USDA every month will make a forecast for how what the crop yields are going to be in the United States. And we can check historically, basically how well our model did compared to USDA. So here's an example of how the model did from 2009 to 2015. What we do is, say, in 2015, we take all the data up to 2014, we fit a model, and then we try to see how well the predictions are going to be for that month in that year. So this is showing that if you try to make predictions in July, on average, you get an error of about 5%, 5.6%. So not great, but not terrible. USDA doesn't even try to make predictions in July. Now, if you look at August, now we can start to compare to how well USDA's forecasts were historically when they were made in August. And you can see that our model that is just looking at satellite images is actually doing slightly better than USDA. It's getting something like an average of 3.3% error. In September, again, we do slightly better, something like 3.4% error versus 4%. Then eventually in October, USDA starts doing better. We get something like 2.5, we still get 3.2% error on average. And so that's not unexpected. What USDA does is they actually go in the fields, they collect samples, they call the farmers. It's a very, very expensive and not really scalable approach. But what we do is we just get images, we feed them into the model, we train our system to basically track plant growth over time and make predictions. So it's a much more scalable, much more inexpensive way to approach the problem. Yeah.
And how would you rate the technical difficulty of this? I mean, obviously you would say, oh, it's very hard and you're brilliant, but in terms of what you're doing, have you found it to be like, oh, that wasn't actually that hard, or like, wow, this is like super hard?
Oh, it depends. I mean, it took a while to work it out. The initial models didn't work too well.
Yeah.
But basically, maybe 6 months worth of work, something like that.
And what kind of compute intensity are you talking?
The data is huge, especially if you want to do it at the US level. In terms of computation, like training these models, you need GPUs, which are not cheap, but it's not too expensive. And after you train a model, then deploying it is pretty cheap.
Okay.
Yeah. And so, here you can see an animation of this thing. It changes the prediction. Back to how hard or easy it is, we submitted it to this World Bank Big Data Innovation Challenge. It's a big competition with hundreds of submissions from all over the world. We actually won the first place, so I think they thought it's pretty impressive, pretty hard. And so we're pretty excited about the accuracy that we got at the end. We extended the model. This is a recent map that I got that we produced in Brazil. It works really well there too. Argentina. We have extended it to India. The next thing that we're going to try to do is extend it to Africa. That's a much harder problem, again, because we don't have a lot of training data. Like the US is good, that's where we started, because there's a lot of historical data and it's clean and it's good. So it's easier to develop models there. But ultimately what we want to do is we want to apply these models to developing countries. We want to build the systems that can track agricultural productivity with very high spatial and temporal resolution. And so we can deploy them, we can help farmers, we can provide them better insurance products and a lot of kind of like downstream applications of this kind of data that is basically missing at the moment. Like nobody really knows anything about agricultural productivity, say in Africa. And so right now we're playing around with this idea of doing transfer learning, see how can we take the knowledge that the models sort of like learned by solving this task in the US or in South America or in India, and then extend it and apply it to in this kind of like data poor contexts like Africa. Other things that we're looking into is we did some work on monitoring crop diseases, some fun results that it turns out that you can also predict them before sort of like the outbreak occurs pretty accurately again from space. Not going to talk much about that. Instead, I'll tell a little bit about some ongoing work on predicting infrastructure quality. Turns out that's another thing that for which we have very, very limited data. We really don't know, where people have access to electricity or not, quality of, say, transportation infrastructure, things like that. We have very, very little data in developing countries like Africa. So what we did is we took sort of like the most comprehensive survey that is available today, the Afrobarometer survey. Contains maybe 20 or 30 countries in Africa, and for some locations, basically they went around and they did surveys and they checked whether people have access to electricity or not, they have pipe water, access to sewage, garbage collection, these kind of things. And then, this is the kind of, let's say if you want to see whether there is access to electricity or not, this is the kind of data that you get by looking at this Afrobarometer survey. Now we try to see to what extent we can predict it just by looking at images of these locations. And you can see this is the kind of map that you get if you were to make predictions using our model, which is again sort of like a pretty global model. It's the same model applied to many different countries in Africa. You can see it's doing pretty well. We can do electricity, we can do access to sewage, we can do access to pipe water, several other kind of metrics of infrastructure quality, and it does pretty well. It's not perfect as you would expect, but it's doing reasonably well. So we're pretty excited about scaling this up and filling in the gaps, so like filling in a whole map for the entire continent. And so yeah, I think that was pretty much it. I hope I convinced you that there's a lot we can do by combining satellite data with machine learning. It's kind of like a really, really exciting time, I think, to think about these problems, both because the data is getting so good and cheaper, and so it's kind of like going in the right direction, and machine learning is getting good enough that we can actually make sense of this data in a scalable way. So it's a really great time to think about what we can do by putting together these two things. I think we're not too far from the possibility of building a system that can sort of track the health of our planet almost in real time by combining all kinds of data. Here I talk mostly about satellite images, but you could imagine incorporating social media data, phone metadata, all kinds of other things that are sort of all kinds of other data sources that are sort of like collected in a passive way. They're cheap, they're widely available, globally available. They contain a lot of information. I think if we combine them with machine learning systems, we can build these really, really powerful models that we'll be able to use to track how we're doing, how to measure all these various measure progress towards the sustainability goals that we all care about. In general, I think it's from also a practical point of view, it's going to be very, very impactful because currently there's very, very little accountability in the whole development sector. Nobody really knows whether money is well spent or not, whether policies are working or not. And part of the reason is that there is no data. It's too expensive to get the data. So if we can provide government organizations, so NGOs and foundations with tools so they can quickly and easily track the campaigns that they do, the policies that they implement, I think we can really have a big impact on how we, sort of like coming up with more effective solutions to these problems. And that's it.
So yeah, I just want to say thank you again. I'm really glad that, as part of this series, we're not only talking about how AI is identifying cats and dogs, but also how we're saving the world, thanks to Stefano's research. And I just want to say thank you again to everyone who came. This is South Park Commons. We're essentially a community of technologists trying to figure out what to do with our lives next, where to direct that ambition, hopefully also make some positive changes in the world. If you want to stick around, we have some more food in the kitchen over here. Or if you want to, talk to Stefano more for a Q&A later. But yeah, thank you all for coming.
Thanks.